Hello everyone, my name is Carlo Giacometti and I work in the audio processing team, and I will be talking about audio synthesis. So how to generate an audio signal. And so first of all, I want to introduce some basic concepts and functions that we will use throughout the whole talk and also the following one. So I will load up 3 examples of audio signals. They are very basic. We have one piano sound, which is not playing. It's very feeble. Can I get more volume? Perfect. So this is a typical harmonic sound, you could call it. I have a collection of bells, which are characteristically inharmonic sounds, and then a bit of the drums that Shadi was playing before. These are typical impulsive sounds that we have. So one function that we'll use a lot for visualization that for sure you have seen already is audio plot. With this, we visualize the waveform of the signal. Another very important function is periodogram. With this, we get the power spectrum of the signal. The Y scale is in decibels, so we can see all the important dynamic range of the signal. You can see, by the way, the first periodogram corresponds to the harmonic signal. You can see there are some very specific peaks, and the positions of all the peaks are multiple integers of the position of the first one. This is the kind of the definition of a harmonic one. The second one also has a set of peaks, which are not particularly, the position of which are not particularly related to each other. The last one looks almost like noise. The last tool that is very important is the spectrogram. It's based on the short-time Fourier transform. We have the time on the x-axis and the frequency on the y-axis. So these are the basic concepts that we will need. Now, first of all, how do we create an audio object? You probably have seen this in the introduction talk. I just want to give a quick recap. So we can import either in core or out of core an existing audio file, and this works fairly nicely. We can create an audio from a sound object. This also works very nicely. We can feed the audio function a table of values. In this case, I am creating a table of a lot of random real values between -1 and 1. This is white noise. The other option, well, this was fairly loud, sorry about that. The other option, which is the one that we will focus on now, is use the audio generator function. In this case, I am simply generating a sinusoid at the default frequency of 440 Hz. This is the most boring sound ever. So how can we make this slightly more interesting? So first of all, let's look at how audio oscillator works. We have a set of basic waveforms that we can use. It's the main ones that are used in analog audio synthesis. So we have sinusoid, triangle wave, sawtooth, square, etc., etc. And here you can see the characteristics of some of them. So a sinusoid is very boring, has one peak. All of the other ones start to acquire more peaks in the periodogram. By the way, is this big enough? Can you all see? So, OK, so we could say audio generator of sawtooth, and we are stuck with a frequency. Actually, no, we can modulate both the frequency and the phase of the signal. And this is the important code to generate what's in the plot here. So we can easily move the frequency and the phase of whatever wave we are generating. Side note, the frequency can be negative. This just gives an inversion of phase. Now, audio generator is not limited to harmonic sounds. We can also generate noise signals. And we have different kind of noises. So the most basic one is the white noise, which has a flat frequency response. But we can delve into all the colored kind of noise where the frequency response depends on 1 over f, the frequency to some power. We have pink and brown noise, where the focus is on low frequency, blue noise, where the focus is on high frequency. But we can also have a more general distribution. We can control the alpha parameter in the distribution of frequency by using audio generator of color and specifying this alpha parameter. So we can change fairly effectively the spectrum of this resulting signal. And this goes all the way from blue to brown, or red, however you want to call it. Now we have a bit more freedom as well with audio generator. We can have a random, any of the random processes existing in Mathematica as an input. Here I'm just using a fractional Gaussian noise. Still boring. But the fact that we can use any of the processes already existing in the language is very exciting. Another possible input is a time series. Here I am generating a realization of fractional Brownian motion. And so the result is a time series. And this can be fed directly into audio generator. So this gives us freedom to throw big time series directly into audio objects. So here I have, I query the wind speed data object. I will not run it right now because I don't think I have an internet connection at the moment. But I did evaluate this previously. So it's just the values of this time series scaled to fit a proper time range. And they are simply used as values for our audio signal. And more exciting stuff that was already possible with play and sample sound function. We can input a pure function and generate an audio signal from that. OK, so these are, we have seen noises, basic oscillators. These are all simple signals. How can we make them more interesting? One classic technique is subtractive synthesis. The whole idea is to start with a complex waveform and pass it through filters to modify the spectral content. In the old days of analog electronics, this was achieved by big things, modular synthesizers like this thing. So you had an oscillator module and a filter module. You would take a cable and plug the cable in the oscillator, plug it in the filter, and so then you get your resulting signal. In Mathematica, it seems to be fairly easier than that. With this single line of code, I generate a sawtooth and filter it with a low-pass filter. And here we can see what effect a low-pass filter has on a sawtooth wave. You can see both the spectrum and the waveform changing. Same thing with a high-pass filter. Like Shadi was saying, we have a big suite for signal processing. And we have a big collection of analog filter models. And we can simply use those. We just need to take care of transforming them to discrete time models. But then we can use any of with recurrence filter directly on an audio object. So this is a way of creating more complex spectra, as you can see, and more complex waveform than basic oscillators. Now, there is kind of the opposite approach. Instead of having a complex waveform and filtering it, we can just add harmonic components made up by very simple sinusoids. So here, I just generate a table of frequency. They are all harmonic frequencies. The fundamental frequency is 200. And I just generate a random vector of a random list of amplitudes. And I can just generate sinusoids with the specified frequencies and the specified amplitudes and just take the mean of those. And I get a waveform with a complex spectrum. Now, we are not limited, of course, to harmonic signals. Now, if instead of a list of harmonic frequencies, I just give a random list of frequencies, the result is much more unpredictable. More similar to sounds that are characteristics of bells and this kind of inharmonic objects. Other techniques, one that Shadi showed quickly, is amplitude modulation. I have two signals, and one modulates the amplitude of the other. So here I have a triangle wave and a sinusoid. And the multiplication, this is the fantastic thing about audio in the Wolfram language. I just need to do a multiplication and a sum, and I get this depends on taste, but this is definitely a more complex result. And you can look at the spectrum. We have the carrier that has its harmonic frequencies. These are odd harmonics. The modulator is a simple sinusoid, has a single peak. And this amplitude modulation process, for each peak of the carrier, creates a couple of sidebands. And the distance between the main frequency and the sidebands corresponds to the frequency of the modulating signal. Same kind of components, but very different result, is frequency modulation. We still have a carrier and a modulator, but now the modulator is controlling the frequency, not the amplitude of the carrier. So to achieve this, we have, Shadi mentioned how we are trying to have as many as time-varying arguments as possible. So take this, for example. Here I have the modal specification, and the second argument in this list is supposed to be the frequency specification. Now, this frequency specification is at all effects an audio object. I can evaluate this in place, and you can see this is now my frequency specification for this audio generator object. And it's a sinusoid slowly varying. This will give us a very slow vibrato effect. Now, okay, this is not overly interesting, but the frequency of this modulating signal now can be raised to the audio range. And this starts to produce much more complex inharmonic sound. This is the basic algorithm on which the famous Yamaha DX7 synthesizer is built on, essentially. And so we have two parameters to control to shape the spectrum of our signal. We can change the modulation frequency, and we can change the modulation index that tells us how much of this modulation is happening. And you can see I am varying the modulation index. And the bigger it is, the more sidebands appear. I can change the modulation frequency, and this instead affects the locations of these sidebands. Now, it is fairly difficult to think of a sound and figuring out how to produce it with frequency modulation. The result is, it is not unpredictable, but it's very difficult to visualize. One easy way to start, I guess, is if the ratio between the carrier frequency and the modulating frequency is an integer ratio, we get a harmonic sound. Here we have several examples. You can see these are all harmonic spectra. I will just play one of them. It sounds fairly harmonic. If instead we use something that's not, that's irrational, like pi or square root of 2 or the golden ratio, we get highly inharmonic spectra. And this is one of the many noisy examples. Now, I showed at the beginning of this slide how I can have a time-varying argument here. But there's nothing stopping me for putting in this nested modulator another modulator. So I could have nested modulations. Here, with this example, I have a sinusoid which is modulated by a slowly varying sinusoidal signal. So this gets us a more dynamic sound that's evolving with time. Until now, we always had static sounds. They were not changing, nothing interesting was happening. This way, we can add some life to it, well, some variation to it. And you can see what's happening by visualizing on a spectrogram whenever that will compute. Here we go. OK. So another strategy that's kind of unique to Mathematica, well, the generation of this is unique in Mathematica, is a convenient thing is to, let's say we choose a physical system. In this case, I chose a vibrating damped string. In Mathematica, we can easily define a system, a differential equation or a system of differential equations, and solve them. So this is what this code does. This will take a bit of time because in the solution there will be many oscillations given the time scale and the selected frequency. So it will take a bit of time. But then what can we do apart from plotting the result of curves is evaluating this function, this interpolating function, and just feeding the data into an audio object. So eventually, when this will here we go. So in this case, the x position, the x parameter that I have in these manipulates is the positions at which I am sensing the vibration. If any of you plays electric guitar, this is equivalent to the position of a pickup, essentially. And the sound is not dramatically different. The model is very simple. It's just a damped string, so not particularly exciting. But we do get a sound, and we are able to change the spectral content by moving, essentially, the sensing position. Now, here we have some less scientific but more fun examples, let's say. So here I am just controlling the frequency of my sinusoidal oscillator, which is in itself very boring. I am grabbing the digits of pi, and I am converting them in base 24. And I'm just controlling the frequency of the oscillator with these numbers. The sequence is fairly unpredictable. If we want something more predictable that shows some patterns, I use here a rational number. Here we go. And here we have a constant pattern. So we can play with this kind of sonification of data, let's say. Another interesting example, this is a function that uses exclusively bitwise operations. And so looking at it, there is nothing special or interesting about this. Turns out that this kind of constructs can produce very complex structures. You can see a rhythmic structure and almost a harmonic structure as well, and some variations. This is a silly example, but it's definitely something one can do. So here I grab the text from the Aeneid in Latin, and I can just transform the characters into numbers and play those. As expected, there's fairly much white noise. So another fun example. Let's see if the internet helps me here. I can grab some financial data. Actually, I have the data here. Let me, instead of connecting to the internet, and who knows what happens. This should work fairly nicely. Okay. And here, I am just controlling the frequencies of a vector of sinusoidal oscillators with these audio data. So I can sonify some kind of market data. In this case, and I can control the volume of the relative intensity for the various companies. In this case, we are listening to the stock price of Microsoft. But we could add Apple or General Electronics, and we can listen to them together. So we can have a sense of the evolution of the stock prices. This is another interesting experiment. So I showed you many spectrograms. It is an image, and we can manipulate it. Shadi showed some transformations, but the problem here that I want to show is slightly different. So here we have a simple image. What if this image was the spectrogram of a sound? How would that sound? How could we generate a sound that produces this spectrogram? So let's grab some images. This code is not overly interesting, but essentially does that. The whole idea is I generate a matrix of complex values, and I control the amplitudes of those with the values in the image, and I do the inverse transformation. So let's compute that for the images we have. Let's display them. Here we go. So we have the image and the corresponding sound. I will play a couple of them randomly. And as expected, they sound fairly weird. And all of those have very different characteristics from each other. Now, let's check that I didn't promise something that I didn't deliver. Let's check that I actually got the same image that I showed here. Let's see if this worked. Same monkey. I think it worked. OK, I think this is it for synthesis.